Hi everyone. This is the lecture 3 for the chapter 4 on optimal receiver for AWGN channel. This lecture 3 will be on the optimal detection and the error probability for band limited and power limited signals. And because this lecture 3 is longer, the contents is longer, so we will split this lecture 3 into two parts, 3.1 and 3.2. And in 3.1 we will discuss the error probability for three modulations: binary PA modulations, binary orthogonal signals, and the binary M-array orthogonal signals. So that would be for the lecture 3.1. And in the another lecture 3.2, we will continue on the discussion of the optimal detection and the probability for another three modulations that are these are the M-array PAM, M-array PSK, and M-array QAM. And at the end of this lecture, we're going to have the comparison of digital modulations among these different digital modulations. So all these digital modulations in lecture 3 are all memoryless digital modulations. For modulation with memory and for non-coherent modulations, we will cover that in the lecture 4. Okay, let's begin with this lecture about the what do we mean by optimal detection and the error probability. We have discussed the general rules about optimal detection. Let's remember that would be the MAP detections that makes this optimal receiver. So today we're going to have use the examples of digital modulations and discuss the error probability. The error probability would be different for different modulations, given the optimal MAP detector. Okay, so the first example we're going to discuss for the optimal detection is this so-called binary PAM, or binary antipodal signaling, or similarly, equivalently, the BPSK. They are all the same. Okay, the binary PAM. So suppose we have these two signals, S1T and S2T. Okay, and is binary signaling is positive A or negative A for the represent the bit 1 and 0 during the bit time. So every signal of S1T or S2T represent 1 bit. So it's binary signaling. So this is as we know, this is an one-dimensional signal with the basis function phi t, that is gt cosine 2 pi fct, one-dimensional basis, and the projection of the signal waveform S1T and S2T on the basis would be S1 and the S2. Okay, the projection on of S1T onto the basis would be square root of EB, and the projection of S2T onto the basis would be negative square root of EB. So EB represent the energy. Okay, EB represent the energy of the of the signal the energy per bit, or here is the equivalent to energy of the symbol. Okay, so the received signal, okay, would be either S1 or S2. Right, the received signal would be positive or negative. So it's binary or it's antipodal. And the received signal would be this ST. ST would be either S1T or S2T plus the noise NT. And after the decorrelator, remember what we have in the receiver. The first part would be always the decorrelator, right? That convert this signal waveform into the vector form. Here the vector form is the one-dimensional because we have one-dimensional basis, right? Okay, so here the received signal that contains R equal to S plus N, and this S would be antipodal. That means that it's binary with positive or negative square root of EB if S1 or S2 is transmitted. And the noise is supposed to be Gaussian AWGN noise with zero mean and the variance of N0 over 2. Okay, so that would be the signal model of the binary PAM. So R would be after the correlator, and R would be the input to the MAP detector. Okay, R is the MAP detector, and S would be the signal part, and the N would be the noise part. So the detection, the optimal detection would be based on R, okay, based on the received signal R, and try to make a decision of the S. And S could be either S1, could be either S2, but the receiver, but we don't know. Okay, we don't know that all the receiver has is the signal R, and the N could be N is a noise that could be a positive value, could be a negative value. It's a Gaussian distribution, so N is possible that for this noise N that change the sign of the transmit signal. Okay, and so it based on the value of the R, we need to make the optimal detection whether this S would be S1 or S2. Okay, now we apply this MAP detector to make the optimum detection, make the best decision of the estimate of S. Okay, here S could be two possible values, S1 or S2, M equal to 2. And the MAP, as we have described in the previous lecture, the general rule of the MAP detector is based on this conditional probability, right? Conditional on the received signal R, right? The probability of the conditional probability based on the received signal R, and what would be the maximum probability of S. Any S, right? Either S1 or S2 that has the maximum conditional probability, then this S, either S1 or S2, would be selected as the optimum detection result. Okay, so you may wonder how to find this conditional probability, right? How to find this conditional probability? We don't know, right? This conditional probability is based on the received signal R. All the clues at the receiver is the value of the received signal R. So it's similar to the Cinderella story, that there is a shoe left by the Cinderella at the party. And this shoe that left over in the party, that is the received signal. So based on this received signal R, that is the shoes, right? That is the shoe. And then we try to find the candidate that has the best fitness to the shoe. Now, there could be many different candidates, right? That we don't know who owns these shoes, okay? And so we try to have all the candidates try to try on the shoes, to try on the shoe and see which candidate has the highest probability that is the owner of these shoes. Okay, and the perfect fit of the candidate, okay, the perfect fit of the candidate, that would be our answer of the detection, right? Okay. So the fitness, okay, the fitness of the candidate to the shoe, that would be this conditional probability. Okay. So you may ask the question, okay, how do I know this conditional probability? This conditional probability, to find this conditional probability is depends on what modulation and what probability model are applied. Okay, so let's rearrange this conditional probability. Okay, this conditional probability is this joint probability of R and S and with over this PR. And PR is the common, as we know, PR is irrelevant to the different source, right? So the PR is removed. So the estimate of S is equivalent to PS times conditional probability of R over S. So given if we given S, PS, the source probability are and the probability model of noise, okay, given this source probability and given the probability model of the noise, and then this prior conditional probability can be obtained based on the received signal value of R. So why do we say this? Okay, this conditional probability of S, that when S is equal to S1, we know the probability distribution of R is the Gaussian distribution with mean value on S1. If S2 was sent, then the probability distribution of R would be a Gaussian distribution with mean value on S2, right? So it would be mean value on S1 or mean value on S2, the Gaussian distribution, right? Either this one or this one. And this curve, we know that these two curves, conditional probability on S1 and S2, we know these two curves. Okay, the probability distribution are over different value of R. If R is a certain value, okay, if the received signal R is certain value, for example, R equal to somewhere here, right? Somewhere here, then we know the probability of the PS2 would be this value. Probability of S1 would be this value. Okay, so if R is here, then the probability of S1 was sent is higher than the probability S2 was sent. However, if R is small on this side, R is small on the left hand side, then probability of being S1 was sent was this, and probability of S2 sent is this, S1 sent is this. So if R is here, it's negative. If R is negative, then the probability of S2 sent would be higher than S1. Okay, so the R, the received signal R, could be any value, right? R could be any value, and however, depends based on the value of R. Is here or here or here or here. Based on the value of R, we could know the which probability, the relative probability of S1 and S2, and then we know whichever is larger. Then we have the estimate of S, right? We have the estimate of S. So this probability model would be available. Okay, would be available. The probability distribution of R given S1 or given S2. Okay, and so if PS is also given, right? So if PS is given, then we have the product of PS and this PS PR over S. Then and hence the PS over R. The conditional probability of PS over R can be obtained, and then we can have the estimate, right? Then we can have the estimate of S. Okay, and this is the MAP detector. Okay, and here if we make further assumption of equal probability of S, okay, if this PS, okay, the source probability could be an equal probability, it could be equal probability, but S is represented here. Whatever the source probability is, we could have the MAP detection result. However, if we further have the assumption of the equal probability of S, that means that the PS1 equal to PS2 equal to 1 over 2. Then this PS could be removed because it's equal probability, and then this detection, this detection is reduced to based on this PR condition of S, the conditional probability on the source. Okay, so we can change this MAP detector with conditional probability on R to the conditional probability on S, and this is the likelihood function. Okay, so this conditional probability, so we have changed the likelihood function of the conditional probability. As we have mentioned the last time, this would be called the maximum likelihood detection. Maximum likelihood detection, and also because the noise is Gaussian, because the noise is Gaussian distributed, right? So this conditional probability can be reformatted by taking the log likelihood function and the distance of the R and SI. The distance of R and SI would determine the maximum likelihood detection. So this ML detection would be equivalent to the minimum distance detection if the Gaussian distribution noise model is provided. Okay, is only if this is Gaussian noise, then we can reduce this Gaussian distribution likelihood function to the distance detection function. Okay, and so this distance detection will be equivalent to the correlation, the correlation of R and S, or the inner product of R and S. However, here the R and S is one-dimensional vector. It's just for the binary. It's a one-dimensional signal, so it's just a pure value. It's the product of R and S when R equal to the product of R and S, which has the which is larger than that gives the detection result. Therefore, we could make the decision. Is decision 1. That means that we make a decision that S1 was sent if this inner product with S1 is larger than inner product with S2, and we make the decision of S2. Okay, if the inner product of R with S2 is larger than the inner product with S1. Please note that this R could be, if R is more close to S2, then R would be a negative value. Okay, then R is higher correlation with S2. Okay, if R is a positive value, then R has a higher correlation with S1. Okay, so in this way, we can obtain the conditional probability or the likelihood function of the detector, right? And based on this likelihood function, that is the conditional probability, then we could make the optimum decision. Okay, so there's only one answer, only one candidate would be the output of the maximum likelihood detector. Next, let's verify the error probability if we apply the MAP detector. What would be the error probability? What would be the resulting error probability? Because we, as we have mentioned, that what do we mean by optimum? What do we mean by optimum detector? The optimum detector means that the detector would minimize the error probability, right? That's what we mean by optimal, right? So now that the MAP detector that minimize the error probability, then we should ask the question, okay, then what would be the error probability that this detector has optimized, right? Okay, that would be a reasonable question to ask, right? So you say this is the optimum detector, then what would be the error probability of the detector? Okay, so let's see the error probability. Say for say S2 was sent, okay, and there is an error. Okay, that means that the estimate, okay, the estimate is S1. However, S2 was sent, right? That would make the error case when S2 was sent. So that would be this case, right? So we have the received signal R, right? And we have the probability distribution of S2 and S1. So when S2 was sent, okay, here, when S2 was sent, what would be the error probability? The error, when does the error occurs? When does the error occurs? The error occurs here, right? When this received signal R has the value that is closer to S1, right? S2 was sent. S2 was sent, but and here this is the decision boundary, right? This is the decision boundary, and the received signal is outside of the decision boundary. On the other side of the decision boundary, okay. So this red area, this area actually is infinite. It's very small till the positive infinite. Okay, so so this red area that would be represent the error probability when S2 was sent. Right, okay? Okay, let's see what would be the error probability. The probability here would be the, as we say, would be this red area, right? What would be this area? As we have mentioned in the chapter 2, this red area actually would be the tail probability, right? The tail probability of this Gaussian distribution function, right? The tail probability of this Gaussian distribution function, that would be represent the error probability of S2. That means that would be the integral, right, of this Gaussian distribution with mean value on the negative side, right? If with mean value on S2, and the tail probability from 0 to infinity, right? That would be the this tail probability. That would be the error of S2. Right, and then we can rewrite this to shift this mean value that we equivalent to this from square root of EV to positive infinite. As we know that this tail probability, as we know, we have learned from chapter 2, right? So for a Gaussian distribution, with mean value of n0, with variance of n0 over 2, so this tail probability would be remember in chapter 2 that what the Q function would be the half of d minimum over the standard deviation of the variance, right? So half of the d minimum would be what? Of the square root of EB, and the variance, right? The variance would be the standard deviation would be square root of n0 over 2. So that we have this error probability of S2, will be this Q function. Okay, remember this is the Q function, okay? And the overall error probability of this binary PM is the point, and the point to point distance of D12. Okay, D12 would be double of square root of EB, right? So then it would be the overall error probability would be the error case of both of all the symbols. The error for S1 and the error for S2, right? And the probability of S1 times the error probability of S1, probability of S2 times the error probability of S2. That would be the overall error probability. So given equal probability of S1 and S2, we have 1 over 2 this Q function and 1 over 2 and this Q function. Okay, then we have the final, okay, we have the final error probability. And this would be equal to the, so actually this would be equal to the D12, okay, the double of square root of ET, D12 over square root of 2 and 0. Okay, that would be, so you can see that we can describe the error probability in terms of EB over N0. Okay, EB over N0 represent the signal to noise ratio, right, per bit. Signal to noise ratio per bit, or the error probability could be determined by the distance of these two symbols, of symbol 1 and symbol 2, right? So the distance would be basically determine the error probability, right? So here you can see that the higher the distance, the larger the distance of the separation of S1 and S2, and what happened to the error probability here? The larger the distance, right? The smaller, right? The smaller the error probability, right? The larger the distance, right? Because this argument represents where the integral starts. Okay, the smaller the x or smaller the D12, okay, the larger the Q function. And the larger the D12, the smaller the tail probability, or the smaller the error. Okay, so the distance determine the error probability. And or you can also say that the signal to noise ratio, EB over N0, determines the error probability. So in general, we can write this error probability in this form. That would be the half of the distance. Okay, it's a Q function, and half of distance over the standard deviation of the noise. Okay, half of distance over the standard deviation of the noise, right? Okay, they are all equivalent, and this would be always true. So if we want to have the error probability in terms of distance and the standard deviation of the noise. Okay, that would apply to different distance and the different variants of the noise model. As the distance goes up, as we said, then the error probability would goes down, right? Okay. Okay, so so far is the binary PAM. Next, let's look at this so-called binary orthogonal signal. The binary orthogonal signal, we have this signal, this two-dimensional signal that has two basis function. So it's binary orthogonal, two orthogonal bases. And then we have this binary, we have a binary two-dimensional signal with two signals, S1 and S2. S1, symbol S1 on phi 1 and symbol S2 on phi 2. Okay, where the base is phi 1 and phi 2. And so for S1, the energy is on phi 1. For S2, the energy is on phi 2. So the received signal is a two-dimensional vector. received signal is also a two-dimensional signal, and is the addition of S and noise. Okay, the noise would be N1 and N2. Noise vector would be N1 on basis 1, N2 on basis 2. If this S is S1, then we have this and the source energy on phi 1. If we have S2 send, then we have the energy on S2, right? And noise N1 and N2. And so now we apply the MAP detector with this received signal R, with this two-dimensional signal R. And then again, we apply the MAP detector based on this vector R, and we try to make a decision of the S and make an estimate, make a decision of the S, what would be this S? Is S1 or S2? Okay, then that so and makes a decision. And this conditional probability based on R would be equivalent to conditional probability based on S. This likelihood function, right? Likelihood function based on R become likelihood function based on S. At what condition? When equal probability, okay? At the assumption when we have equal probable source symbols, PS1 equal to PS2, then we can rewrite this conditional probability to the conditional probability on S. And this conditional probability on S, then and again it becomes the minimum distance detection. If what? At what condition? At the condition when this noise is Gaussian, right? When this noise is Gaussian, then this conditional probability is a Gaussian distribution, and then equivalent to log likelihood function, and the log likelihood function is equivalent to this distance function, right? So when we have this, so be careful when we have this simplification that is based on this assumption. Based on the assumption is equal probable source, or there are some with this only with these assumptions that we can re-express this detection. And then this distance detector become this correlation detector. Okay, and for equal energy source, then we can and here when we can reduce this is because it's equal energy source, because the is the inner product of the received signal with the source. Okay, the inner product of R with the source vector. Then we can so is the so we can further simplify the calculation. Okay, so then we can make a decision on S1 or S2 based on the inner product of these two vectors. The correlation of R is higher on S1, then we have decision on 1. If the correlation of R is higher on S2, then we have the decision of D2. Okay, and then so we have the MAP detector for binary orthogonal signal. And so the next question is what would be the error probability if the MAP detector is applied to this binary orthogonal signal. Okay, so the error of this S2, here is the probability distribution of S2, and the probability error distribution if S1 is sent, and this is R. Given different value of R, the probability distribution if S2 is sent of R. Given the probability distribution of R if S1 was sent, right? So again, the error probability of when S2 was sent, and there is an error when S2 was sent, right? When S2 was sent, then the received signal probability distribution would follow this curve, right? Would follow this curve, and the error occurs when the received signal R is on the other side of the decision boundary. On the other side of the decision boundary, that is this red area. That makes the error case. That means that the R S2 was sent, but the correlation of R on S2 is smaller when S2 was sent, but the correlation of R with S2 is smaller. That would be this. That is this area. By taking the inner product of these two vector and this two vector, right? Then we could have this. That would be that given S2 ascent, the inner product of this R with S2 would be this, right? Inner product of R with S2 would be this. The inner product of R with S1 would be this, because the R has energy on phi 2, right? So the inner product would be this. So that would be the when this inequality occurs, then that makes the error case. So let's rearrange this inequality. This inequality is equivalent to equivalent to n1 minus n2, right? It's equivalent to n1 minus n2 is greater than square root of EB. That would be equivalent. They would be the probability would be equal. They have the same probability. So the question is, what would be the probability of this n1 minus n2 greater than square root of EB? What would be this error probability? To answer this question, then we have to know what would be the probability distribution of n1 minus n2. n1 minus n2 together is a new random variable, right? n1 is a AWGN random variable, Gaussian distribution. n2 is another Gaussian distribution random variable, and the combination of two random variable and the new random variable would be what? The new random variable n1 minus n2 would be a Gaussian distribution with variance that is the sum of these two random variables, right? So this new random variable has a zero mean and the variance of n0. That would double the variance, right? So so what would be the probability of this new variance greater than this value? that would be what? Again, this is the tail probability, right? The square root of EB where the integral starts, and then this standard deviation of the variance, that is square root of n0, right? And that makes the Q function. And this Q function that represent the error, Okay, so the point-to-point distance of D12 and the overall error probability. The overall error probability would be that S1 was sent and is an error, or S2 was sent and it is an error. That gives the overall error probability. If it's equal probable, if we have equal probable source, then we have the error probability here, then we obtain the final overall error probability, right? Overall error probability. That would be that in terms of EB over N0, this Q function, or in terms of the distance, D12 over square root of 2 and 0. So let's know that this Q function, this error probability, if we compare this, right? If you compare this with the previous example, the binary PAM, with the binary PAM, which is larger, which is smaller? Remember in the previous example, in the binary PAM, there's a 2 here, right? Square root of 2 EB, right? So it's larger, right? It's larger, and so this error probability of this error probability is larger than binary PAM. So why this is larger? Why this modulation has larger error probability? Is because the distance, right? The distance of S1 and S2, right? Now becomes what? Now becomes square root of 2. Okay, in the binary PAM, the distance is 2, 2 square root of EB, and this is square root 2, and it was 2. So the distance between S1 and S2 in this case is smaller. Okay, is smaller. Okay, is smaller. So this has it turns out the error probability is higher for binary orthogonal signal. But however, it's all equal to this Q function D12 over square root of 2 and 0. Or again, it's all equal to half of distance over the standard deviation of the noise, right? It's all the same. And because the distance D12 in here becomes smaller, right? D12 become smaller, so the overall Q function become larger. The area, okay, when this D12 becomes smaller, this area become larger, and the tail probability become larger. Okay, so again, as this D12 gets smaller for binary orthogonal signaling, so this error probability become larger. This is what we see here for binary orthogonal signal. Okay, so the next modulation would be the M-array orthogonal signals. That extends the orthogonal signaling from the binary, the two-dimensional signal to m-dimensional signal. Now suppose we have m different symbols, and each symbol has energy on one of the orthogonal bases, and we have m different bases. So that we have on the signal space, we have m-dimensional signal space. Each symbol would be on one of the bases, a vector on one of the bases, and the energy, the symbol energy of each signal would be Es. And as we can see that all the pairwise symbol distance would be the d minimum would be square root of E. And the suppose now suppose the S1 was transmitted. Okay, suppose S1 was the symbol transmitted, and let's see what would be the error probability when S1 was transmitted. Since if S1 was transmitted, okay, and the received signal would have the energy on the basis phi 1. The received signal R is an m-dimensional vector, and R1 has supposed to have the transmitted signal, and R2 to Rm that contains noise only, and so that the conditional probability of R1, the conditional probability of the signal, the first component of the received signal R1, the conditional probability if the vector S1 was transmitted, and the random variable R1 would be Gaussian distribution, right? Would be a Gaussian distribution with mean value on the transmit signal square root of Es, and the variance of N1, right? So the R1 is a random vector, R1 is a random variable, R2 to Rm are all random variables. R2 to Rm are zero mean Gaussian random variables because these are noise, and together we have random vector. So for the rest of the Rk, for k equal k from 2 to m, the random variable Rk, that would be a Gaussian distribution, right? Because these are just noise. Would be zero mean Gaussian distribution random variables. Zero mean Gaussian distribution random variables. So we have R1 is has a mean value. It's a non-zero mean value Gaussian distribution, and R2 to Rm would be zero mean Gaussian distribution. Let's see the MAP detector. That is apply the receive signal to the MAP detector and see what happened. The receive vector, okay, the receive vector has the now we have the receive vector, right? So now we apply the receive vector to the MAP detector as the input to the MAP detector, and see and try to find the estimate of the source. The inner product with each candidate, with each source, right? We have the inner product with source 1 The source 1 has a non-zero value, has a mean value on the source and the noise 1. And the inner product of the receive vector with the with other sources, as k from 2 to m, because the receive vector has for the other for dimensions basis 2 to m, the receive vector contains only noise, right? Only noise, right? And the source is only non-zero on the dimension k, and so that becomes this. So the product that has only that becomes the noise k, and so now we have. So this correlation, we have m different correlation result, and one of them has the largest value. That means that would be the estimate. Then that source would be the estimate result. Then what would be the error probability? If S1 was transmitted. Okay, if S1 was transmitted. And the error probability for S1 was transmitted would be when there are many error cases. It would be when this is the first correlation, right? And there are from k from 2 to m, all the other correlations. If this correlation is largest, then we have an correct detection. If any one of these corrections from k from 2 to m is larger than the first correlation, then we have an error on S1. Any one, right? Or more than one. There could be more than one sources, right? That is greater than the first correlation. So there are many different error cases. So it's difficult to find all the error cases. There are too many. So the easier way to find all the error cases is by from all the probability minus the correct detection probability. The correct detection probability occurs when the first correlation is greater than all the other correlations, right? Then we have an correct estimation detection result. So that means that means correct detection, right? The first correlation is greater than all the other correlation result. Okay, that means that, what does that mean? That means that we have the receive vector R, right? And there's R1, R2 to Rm. That means in this vector R, R1 has to be greater than R2. R2 is N2. And R1 has to be greater than N3. N3 is R3, right? And R1 has to be greater than Rm. That is only noise M, right? So all these cases have to be satisfied at the same time. Then we have a correct detection, right? All this event has to be satisfied. Then we have a correct detection, right? So then what would be the probability, right, of all this event? The joint probability of all this event would be this integral for any received signal R1, the first component in the vector R. This R1 could be any value, right? R1 could be any value because of the noise 1. So R1 could be from minus infinity to positive infinity, right? R1 could be any value with certain probability. It's called PR1. Under this probability of PR1, then we have given R1. Then R1 has to be greater than R2, greater than R3, and so on, greater than Rm. They all has to be satisfied. R1 could be very small, right, with very low probability, of course. But however, no matter what value of R1 is, R1 has to be greater than all the other component of R. That is N2, N3 to Nm. Right. Okay. So let's try to find this probability. Okay, let's find this probability, a closed form of this probability. So let's give when suppose if we have given R1, okay, given R1, then this conditional probability, this conditional probability, given certain value of R1, R, as we said, R1 could be any value. Given this value of R1, then we have this joint probability to be satisfied for correct detection. And this event, the joint probability of these events are independent. These are independent events. Why they are independent events? Because each dimension are orthogonal, right? The N2 is orthogonal, is independent to N3, N4 to Nm. They are all independent, right? Here R is a value, right? R is a scalar value, and N2 is a random variable, and N3 is a random variable, Nm is a random variable. All these random variables and noise are all independent to each other, right? So this joint probability are independent to each other, and so they are separable, right? This joint probability become separable probability function. Okay, the product of this each event, the product of the probability of each event. Okay, so here let's find what would be this the probability of R1 greater than Nk, okay, given R1. Remember, R1 is a value, right? R1 is just a value, and Nk is a random variable. The probability of this random variable Nk less than value R1, right? That's what this means. The probability of random variable Nk less than value R1, right? That would be this integral, right? The probability of the distribution of random variable Nk, right? And Nk from minus infinity to R1. So Nk, that means that Nk is always less than R1, right? Nk is less than R1, right? So the area of this Gaussian integral, right? That would be what? That would be 1 minus the tail probability, right? From this Q function is the tail probability from R1 to infinity, right? This is 1 minus this tail probability would be this value, the integral result, right, is 1 minus the tail probability, right? So we have it here, right? So we have this here. Each of this conditional probability is 1 minus Q function, right? Okay. Okay, therefore we can have the finally have the correct probability given as 1 is this joint probability, and given all the possible value of R1. Okay, then we have it here, this 1 minus Q function, and there are how many events? N minus 1 independent event, and we have the PR1, right? PR1 is a Gaussian distribution function, and DR1, and that gives the correct probability, right? So the error probability, as we said, the error probability of S1 will be 1 minus the correct probability, right? 1 minus the correct probability. That would be this. Okay, so the overall, this is for S1 was sent. In overall, the error probability would be all the possible sources and with the error. LDP, that means the average error probability of all different sources, and as the all the sources are equally probable. Okay, assume if all the sources PSI are equally probable, then this average probability would be become any one of the error probability of the symbol. The average would be equal to the error of each cases, S1. That would be this one. Okay, so it's difficult to catch this error probability here. It's difficult to catch the error probability here. What would be this error probability for different m? So if we take the computer to numerically plot this curve, we can see here for different modulation order of this M array orthogonal signal, for m equal to 2, this m equal to 4, and A 16 and 32. This is error probability of bit error, bit error probability. And here the x-axis is SNR per bit, EB over N0. And here we can see that if we plot this error probability numerically, we can see that as m increases, the error probability, the bit error probability becomes what? Becomes smaller and smaller, right? The bit error probability becomes smaller. That means that as m increase, the bit error probability would decrease as well, right? So here as m increase, we see that means the bit rate increase as well, right? As when m increase, that means every symbol carries more bits for every transmission of the symbol. And also we can see that as m increase, the bit error rate the bit error rate would goes down. The bit error rate, symbol error rate would goes up, but the bit error rate would goes down. The price paid is the bandwidth for MFSK, or the price paid is the complexity, the number of bases. Okay, the symbol error rate would goes up. However, the bit error rate here would goes down. Okay. So what has to pay? What has to pay? As we said, that is the basis for MFSK, or the number of bases, or the what is to pay is the bandwidth. Okay, the last we'd like to discuss is the bit error rate for M-array orthogonal signal, the bit error rate. To compare different modulation schemes for different M values, sometimes it's more fair to convert the symbol error to the bit error rate. Okay, because for different modulation order M, that means that the different number of bits, the larger the M, that means that it carries log 2M, the k bits. So sometimes it's not fair to compare the symbol error, because the number of bits are different. So it's more fair to convert it to the symbol error probability to the bit error probability, or the bit error rate. Let's see what happened in the M-array orthogonal signals. In M-array orthogonal signals, the symbol SM has equal probability of having error to any other symbols, right? Because the distance are all equal for a symbol M to any other symbol, right? The distance are all equal. All the distance are equal to square root of 2e. And so if the error probability, the probability of the M was sent, okay, a symbol M was sent. However, the detection, the estimate, or the decision is SL. If L equal to M, that means we have a correct detection. Then the correct detection probability is 1 minus error probability, PE. PE is what we have in the what we just have for the M-array orthogonal signal, rather that ugly integral. And if the error not equal to M, that means we have an error. The error probability would be PE, and for each cases of L, that would be one of the error cases, right? So that would be PE over M minus 1, because all the other symbol error detection are equally equal distance. So for L not equal to M, this error case probability would be PE over M minus 1. So suppose the SM represent k bits, right? SM k bits, k equal to log 2m. The message is bit 1 to bit k. And symbol SL, the detected symbol also represent k bits. The k bits from the bit 1 to bit k, another k bits, and k equal to log 2m. There are k bits of the transmit information, the transmit message, and there are k bit of the receive message. And for a single bit arrow, there are 2 to the k minus 1 combination of cases for the same symbol arrow. Okay. The bit array of the M-array orthogonal signals. We have discussed the bit array for any m. Let's give an example for m equal to 8, and so that is k equals 3 for example, so we can better explain what happens. So assume that S1 is sent at the transmitter, and there are 8 different symbols, S1, S2, S3, and to S8. We have 8 symbols, and because m equal to 8, each symbol would represent 3 bits. And assume this is the bit mapping of the symbols and the message. And assume S1 was sent. And if the receiver has the correct detection, then the correct detection probability will be 1 minus PE for M-array orthogonal signal. Okay. If the PE is the what we have for the M-array orthogonal signal, the integral and that algorithm integral. And there are 7 error cases, right? If the detected result is any one of these 7 case symbols, then that makes the error. So the error probability occurs when the estimate of the symbol is unequal to S1. Then that is the probability of error. So each error cases are equally probable, right? Because of M-array orthogonal signal. So each error probability would be PE over m minus 1. We have 7 cases, right? So the among these 7 cases, if we look at each bit, right? Look at each bit. The error symbol cases does not necessarily make the bit in error. Does not necessarily make the bit error. For example, that the first bit here, this is 0, and there are 7 error cases, but only 4 out of 7 error cases that would has the penalty of this bit to be error, right? In these 3 cases, even the symbol is error, but the bit is correct, right? Bit is correct. So only 4 out of 7 error cases that makes this bit in error. The same for this bit, the second bit. There are 4 cases out of 7 that has the penalty of bit error. The same here. There are 4 out of 7 cases that has the bit in error. So the bit error probability would be 4 cases out of the each case. Each case has the probability of PE over 7, right? And the four of them that leads to the bit error. So the bit error probability would be this. So in general, given m and k equal to log 2m, then the relation of the bit error rate PB and the symbol error rate PE would be half of m over m minus 1, right? Only half of m would be error cases over this m minus 1 cases, right? So we have this relation of the bit error rate and the symbol error rate. Symbol error rate we already have in the previous derivations. Okay, replace this m with k. Then we have this. Then we have this. The PB and PE in terms of k. Okay, and for different number of m, we can have the relation of the bit error rate and the PE in this table, and so on. Here we can see that when m increase, as m increase, the number of m modulation order m increase, then this bit error rate PB would what happened to this bit error probability? It would decrease, right? It would decrease, right? As m increase, this PB, this PB would actually decrease. And also as m approach to infinite, then this PE would eventually approach to half of the PE. The bit error rate would about the half of the symbol error rate. So again, this figure shows the bit error rate probability over SNR per bit. SNR per bit represent EB over N0, right? EB over N0. So as M increase, right? As M increase, the PB, the bit error rate, right? This is PB. The bit error rate would actually decrease. The PB would drop. Given the SNR per bit, the PB would goes down as M increases. Okay. And the last slide about the MRA orthogonal signals on the union bound of probability of error. Remember, we have derived the approximation of the MRA orthogonal signal error probability, right? That we do not have the closed form of the error probability of the MRA orthogonal signal is an integral, right? It's messy. It's a messy integral, and we could not have the a closed form. We could use computer to numerically simulate the error probability. Okay, but it's not. We do not have the closed form. So here we try to find a union bound, so that we could have simple expression in the closed form to evaluate the simple error probability for this MRL sound signal, so that we could have a quick and better idea of the error instead of the PE we have in the previous slide. Let's have the review of the union rule first. The union rule says that suppose we have several events, event 1, event 2, and event M, then the probability of the union would be less or equal to the summation of the probability of each event, right? That's the union rule, and I think it's very straightforward to understand because the union of the set, right, is less than the summation of the set, right? So based on this rule, we can find the union bound of this error probability. Union bound helps to have a better understanding of the bound of the error. Remember the error probability, that is the average of all the cases of the overall error, is the for every symbol and the symbol error rate of symbol M, right? And we have M different symbols, right? Each symbol has the error probability is the union of all the error cases for when SM was sent. Okay, and if we assume the all the symbol PSM are equally probable, then PSM equal to 1 over M, right? 1 over M, and the sigma and the summation of this PSM, there are M cases, and they are all the same, right? The error probability of each symbol SM are equal. So this summation equal to the case, the union error probability of each symbol. Say symbol S1. Given S1 was sent, the error probability of S1. That means that the correlation of S1 is less than any of the correlation with SL and the union of all the error cases. And by this union rule, the union of all the error cases, the union of the error cases would be less than the summation of each error case, right? The summation of each error case. There are error case when this L equal to 2 to M, right? So there are M minus 1 error cases for if S1 was sent, and there are M minus 1 error cases. And the summation of the error cases would be greater than the union of the error cases, right? Okay, let's try to see. So, and each error cases, right? Each error cases are equal. because this is M array orthogonal signal. So this M minus 1 error cases has the same error probability. So the summation would be equal to M minus 1 multiples of the each error case. Say error case S1 was sent, but the correlation with S2 is greater than correlation with S1. That's one error case. And we have the summation would be the M minus 1 of the error case. And this is, as we know, this error probability is the probability that this R2, right? R2 is greater than R1, right? This is R1 and this is R2, right? The probability of R2 greater than R1, then we have this error case. So, and this is equivalent to the probability that N2 minus N1 greater than square root of Vs, right? That is equal to this probability. And as we have derived that this probability will be, this is Q function, right? This is a random variable that has the area that is greater than this value, square root of ES. So this probability has the variance of the N0. And so this would be a Q function. This is where the integral starts. And this is the standard deviation of N2 minus N1. Okay, so this is the this Q function represents this tail probability. Okay, so here we have the simple upper bound, right? The upper bound represents the error probability of M array orthogonal signal, right? It's much. So we have the a closed form expression, right? Closed form expression for the upper bound, the union bound of error. As here we can see that as M increase, right? As M increase, the error probability increase, right? Increase as well, right? The error bound, union bound increase as well as M increase, right? And it actually depends on ES, whether ES is fixed or not. If ES is fixed, then PE would goes up. If ES is not fixed or E is changing with M, then it could be different. Okay, and also, and then by the Chernoff bound, now recall the Chernoff bound. This Q function is less or equal to this Chernoff bound, the exponential over 2, right? This is the by according to the Chernoff bound. Now then we can re-express this upper bound, the union bound of the error. And this M, we can rewrite this M in terms of K. M equal to 2 to the K. And also this ES equal to K bits of EP, right? The symbol energy equal to K bits of EP. Okay, so we can rewrite this union bound in terms of K. Then this is exponential, right? And this is 2 to the k. That's change all the basis to the natural basis exponential. So this 2 to the k is equal to exponential KLN2 minus 1, and this is the same. Okay, and if we just keep this first term and drop this second term, this minus 1, then we have this then this upper bound is less than this just the first term, because the first term has this exponential, and that combines with this exponential here, and we drop this, so it's less than this term. So it's exponential KLN2 minus KEB over 2N0. Okay, so, and again, this could be also the upper bound or the union bound of the symbol arrow. Okay, so if we look at this union bound, okay, and the arrow would be always less than this union bound, right? The symbol arrow, the MRA orthogonal symbol arrow would be always less than this union bound. And what does this suggest here? What that if we look at this union bound, what does it tell us? Okay, here we can see that if EB over 2N0 is greater than LN2, and this will become negative, right? This exponent become negative value. K is positive integer, and if this EB over N0 is greater than certain value, that means that EB over N0 is greater than 2LN2 or 1.42 here. Is greater than certain value, then we have this to be exponent to be negative. And then as K equal to K approach to infinite, right? K is a positive integer, and this is negative, and if K approach to infinite, then it is possible to have this arrow upper bound to approach to 0, right? That means that it is possible to have the error probability as small as possible. This is called reliable communication requirement. That is this EB over N0, that represents the signal to noise ratio per bit, is greater than certain value. This would be negative, and it is possible to have the symbol error probability that is close, go approaching to 0, as small as possible, right? As long as this SN ratio is large enough, right? Let me say it again. When this SN ratio is above certain value, then it is possible to drive this error probability as small as possible, right? Okay, this is, and however, okay, if this error probability is smaller than LN2, then this upper bound could be greater than 1 because of this, then because this become positive and k is a positive integer, and the whole thing become greater than 1, right? So we cannot guarantee anything. The error probability could be very high, right? If then this error upper bound could be greater than 1, that means that this error probability could be very high. So we cannot, we have no control of the error probability if this SN ratio is smaller than 2ln2, right? However, if SN ratio is greater than 2ln2, then we could control the error probability to be as small as possible. Okay, so this is very important. Okay, it's very important for the to see the signal to noise ratio requirement for reliable communication. So this is true for MRA orthogonal signals. Okay, let's stop here for the first part of lecture 3, and we will let's have a break, and then we will have the second part of the lecture 3.